Hi everyone, so as always we start with the learning objectives, which are here. Feel free to go through them, or if you want to wait until the end, I will put them up again in the last slide. Okay, so hopefully all of you have seen a glass in your lives, and all of you know that if I do this to it, a sound is made. So what we're going to do in the next slide is try to figure out how this sound is actually made and what it is. So here's a short video to show you what's actually going on. I have a hammer and a ruler, and I'm going to hit this ruler with the hammer. And then the ruler is going to start to vibrate back and forth. Now every time it vibrates, it's going to push the air molecules around it, and then it's going to create a difference in density. This difference in density, and therefore in pressure, is going to propagate itself like this, just as in a wave. So as you can see, this vibrates, then the molecules push each other, creating a difference in density and therefore in pressure, which is just a wave. And then these waves go to our ears and hit our eardrum, and that's how we hear the sound. Okay, so here's a question for you. If we know that sound is just particles pushing each other, then can sound travel through vacuum? And please give me a reason for your answer. Answer in the comment section, and that's how I will know that you've watched the video. So unfortunately, we humans cannot hear every possible sound in the universe. We have a range of frequencies that we can hear. Now, in this graphic made by me, and I'm sure you can guess which of the drawings was the one that I made, you can see the human hearing range, which goes from here to here. So from 20 Hertz to 20,000 Hertz. Anything higher than 20,000 Hertz, we can't hear it, and we call it an ultrasound. But bats, for example, they can hear it. Anything under 20 Hertz, it's an infrasound, and we also cannot hear it. But for example, elephants can hear it. Okay, so knowing what you know about sound being just a push that gets spread out in a gas, in a liquid, or a solid, just molecules pushing each other, I would like you to try to guess where sound travels faster. Does it travel faster in gas, where molecules are very spread out, in liquid, where they're closer together, or in a solid, where they're packed really, really tight? Now, I will give you the answer in the next slide, but I would like you to do the thinking for yourself. So please pause the video, think, and then look. I said think. Okay. Okay, so hopefully you did the thinking for yourself and you reached some sort of conclusion, and here's the right answer. Now, if you didn't get it right, that's perfectly fine, because if you already knew everything, there would be no point in me teaching you. So in a gas, molecules are very spread out, which means that for this guy to push the next guy, it takes a while. And because of this, sound spreads much slower than, for example, in a liquid. So this is the average speed of sound in air. This doesn't mean that it's always the same speed. So for example, at different temperatures you will have different speeds. This is the average speed of sound in a liquid, and again, depending on the liquid, it will be higher or lower, but this is just more or less. You can see that this is much higher than this. And in a solid, it's even faster. And that makes sense, right? Because when, I don't know, a bunch of people are all together and I push one of them, then the push gets spread out really, really, really quickly because people are in contact. Whereas if the people are spread out and I push one of them, then it takes for a very long while for the guy on the other end of the room to feel the push. Okay, so now I would like you to think about how you would measure the speed of sound in air. So think, which devices would you use? How would you calculate the speed of sound? Pause the video and think, and then I will show you the answer. Alright, so hopefully you did your thinking. And here you can see a device that can be used to measure the speed of sound in air. This does not mean this is the only possibility. That's just one possibility that you could use. So you get two microphones separated a certain distance, and then you make a sound, and then of course they will record the sound at different times. Then you record the difference, and then distance divided by time, that's the speed of sound. Piece of cake. what I would like to discuss now is the relationship between frequency and pitch. Now, you know that this sound, for example, has a lower pitch than this one, and a lower pitch than this one, and so on. And what happens really is that the lower the frequency, the lower the pitch, and the higher the frequency, the higher the pitch. Now, there's also a very interesting phenomenon, which is when two notes are separated by an octave, so for example this one and this one, they almost sound like the same note. And why is this happening? And the answer is that their frequencies are in a very, very particular relationship. One frequency is exactly twice the other one. Let me show you in a drawing. Okay, so we just said that the more the frequency, the more the pitch. So here I have a wave with a certain pitch, and of course a certain frequency that, as I told you, is related to the pitch. Now I would like you to think, how would you draw a wave that has a higher pitch? Well, if you listen to what I said before, higher pitch means higher frequency, so we just draw a wave that repeats itself more often. So this wave here has a higher frequency and therefore a higher pitch than this wave here. Piece of cake. Now, how about a wave that's exactly twice the frequency? Remember, an octave higher than this wave here. Well, in this case, let's try to draw this on top. The idea is that the wave should repeat itself twice as often as this guy. So in this space here, I should be able to put two waves. Let's try that out. So again, what I want is a wave that starts in the same place and ends exactly in the same place. Now, there you go. Can you see how here, for one of these crests, I have two of these ones. For one of these troughs, I have two of these ones. But they start in the same place and they end in the same place. Therefore, this wave here has twice the frequency of this one. If I kept doing this for the rest of the wave, then I would get a wave that's exactly twice the frequency of this one. So this wave is exactly 1 octave higher than this sound wave. So how about loudness? So this note here is the same pitch as this one, but of course there's a difference, right? So how would we draw this difference? Well, in this case, the frequency is the same, which means that if one wave looks like this, the other one will have crests and troughs just as frequently. But the amplitude is different, which means that the other wave is going to look something like this. Now, as you can see, the crests and the troughs are exactly at the same spot. It's just that these ones are much higher than these ones. And remember that the amplitude is the difference between here and here. So a wave that's louder than another will have a higher amplitude. Now, of these two waves, the black one and the red one, which one is the loudest? Obviously, the red one is the loudest. And which one has the higher pitch? Well, since they all repeat at exactly the same time, the pitch is exactly the same. So these are two waves with the same pitch, but different loudnesses. And the red one is louder than the black one. Okay, now we're almost done, and I just want to speak a little bit about echo. And hopefully you all know what echo is. So here's me, and here's a wall, and then I make a sound, and then the sound comes back to me because it reflects at the wall. So it reflects and then comes back to me, right? Now, for example, if I know how long the sound takes to come back to me, I could figure out how far the wall is if I know the speed of sound in air, right? Because I would know the speed, I would know the time, and therefore I could figure out the distance. And since I know this has gone back and forth, then I will know exactly how far this is. So this has a lot of applications. For example, sonar. Now sonar is something that submarines have, where, well, let me just draw a submarine. Okay, that's not a great submarine. And what they do is they keep emitting these ultrasounds and see if they come back. So imagine that there's a little ship here, and then the ultrasound comes back. Then it gets registered by a submarine, and then because they know exactly how long it took to come back, they know that there's a ship at a certain distance, and then you can use this to, well, blow them out of the sky. Another use of this is ultrasounds. Now, an ultrasound, as you know, is a sound that has a higher pitch than we can hear, but at the same time, it can also be used to take a look at things inside your body. So imagine that here's you, and then I put this little device here that starts emitting ultrasounds, and then these ultrasounds get reflected by things inside your body, like your stomach or your liver or your bones. And then by taking a look at the shape of the sounds that come back to me, I can make an image of what's inside your body. And that's how you can see babies before they're born, for example. So let's take a final look at the learning objectives, and these are taken straight away from the IGCSE. So describe the production of sound by vibrating sources. Tick, we've done that with a ruler. Now, you also know the approximate human range of audible frequencies, hopefully, from 20 to 20,000 hertz. Then, demonstrate understanding that a medium is needed to transmit sound waves. Tick. You should know that sound cannot travel through vacuum, for example. We've done this. We've determined an experiment to determine the speed of sound in air. And we know how loudness and pitch are related to frequency. We know about echo. Now, this we did the last day, but hopefully you should be able to remember this. And we also know that sound is a change of density that travels. Therefore, there's a compression and there's a rarefaction. Now, rarefaction is just the opposite of compression. So when things get more spread out, that's a rarefaction. And finally, you should also be able to state the order of magnitude, which means just an approximate number of the speed of sound in air, liquids, and solids. Remember that this was around 330 meters per second, this was around 1,400 meters per second, and this was around 5,000 meters per second. If you can do all this, you can do everything that the IGCSE wants you to do, and you should be fine for the exam.